It's time. The show is starting. Planetarium Live. Yes, episode 3. We're gonna do some more Universe Sandbox today. I'm really looking forward to that. We're gonna have a lot of fun exploding things, firing stuff at other stuff. Hopefully, getting a good quality stream going. I know last week we had a little bit of trouble trying the YouTube thing again this week. And I should say last time was on Tuesday, and we had a bit of trouble using YouTube. So we're going to try it again with YouTube, and hopefully it works out really well. And if so, then we can blame Jesse for the roughness of the stream last week and try it again. However, next stream on Tuesday, Jesse is going to join us again, so that'll be a lot of fun. So let me say hello. There's me. It's nice to see you. Thank you for coming out on this lovely Saturday night when I'm sure there's a lot of other fun things to do. I know that they're playing old hockey streams of classic Leaf games on TV right now, which is kind of cool. But I'm glad you decided to spend some of your time with me for some space stuff. We're going to have, like I said, a lot of fun. We're going to bring up Universe Sandbox. We're going to talk about a few things. We're going to blow some stuff up, send some stuff toward the moon and the Earth. And then we're going to talk about planets around other stars, also known as exoplanets. How do we find them? We're going to take a look at a couple of examples where we find them and why they're really exciting and important. And last of all, the special treat, we're going to talk about black holes. Just a little bit. I'm not going to go too deep into the world of black holes, but we're going to talk about what they are, how we find them, and why they're notoriously tough to find. And the hint is that they're black holes. They're dark. They're hard to see. Okay. So we're going to bring up our Universe Sandbox and start our stream. We've got our first we want to know already from the chat, so we're gonna go over to Universe Sandbox, and that's from Jen. Oh, Lucas wants to know what happens to us, the Earth, if the moon crashes into us. Well, I'm so glad you asked. Why don't we just do that? Why don't we just get right there and dive right into it? I'm just gonna move this over. Let's get the moon. And we're going to launch the moon directly toward the Earth from far away. So here we go. Let's line up our target. Ready, aim, fire. Now, of course, it's not moving yet because we're going to play it. We're going to watch this in nice, slow motion. We're going to slow it right down and watch the moon slowly work its way in toward the Earth and see what it looks like if the moon were to crash into Earth. The caveat is this is actually impossible. But, hey, here's what it will go. Well, that was kind of expected, right? We see a giant moon-sized crater in the Earth. It would be a little bit messier than this. I'm gonna pause this for just a second. Earth looks a little bit worse for wear. I think we've seen the Earth have better days, but in this case, it appears about half the Earth is now covered in fire. The surface temperature of the Earth is going to climb up to, well, let's take a closer look here. The average surface temperature of the Earth is now 710 degrees Celsius, which is a little bit hotter than a typical summertime on the equator, but yeah, not really survivable either. So not a very nice thing to check out. But when all these bits of the moon bounce around, not only do we end up with one giant moon-sized crater, we also end up with a lot of other craters spitting around the Earth, and you can see them poking holes in the ice over here. So we're gonna start this again, but we're actually gonna bring up a new simulation. We're gonna bring up the moon, and the reason we're gonna bring up the moon is that we're gonna start to crash a few things into it. Because that's kind of cool. So here's our moon right there, and we're going to crash some small stuff into the moon. There was actually a period very early on after the moon formed, about 4.5 billion years ago, that this era of what was called bombardment happened. And we're going to select random asteroids, and we're going to just fire some asteroids at the moon. And this is kind of what happened, is that a bunch of random asteroids kind of smashed into the moon all at once. Oh, well, I say all at once, but it was really over a period of about, let's get some bigger stuff too. Yeah, there we go. It was really over a period of about 1 billion years after the Earth and the Moon formed, and there's actually a really good simulation on that we'll be able to find here. So we're going to say moon, it's moon bombardment. Let's bring it up. There we go. Bombardment of the moon. So this is really fun, because we're actually going to see a bunch of stuff crash into the moon right now. And you see all those dark regions on the moon, if we zoom in a little bit, aside from the giant craters falling into them, those dark regions are all there because of impacts like this that happened billions of years ago. These giant rocks left over from the early solar system smashed into the moon and the Earth and basically every other planet that's in our solar system. All that leftover rock from the formation of the sun smashed into the moon and left these big craters. Now back then the moon actually had lava, it had magma underneath the surface. It wasn't one solid chunk of rock like it is today. And so those big holes in the moon actually filled up with lava. They filled up with lava. That lava over time cooled, solidified, and gave us these big dark regions. So I'm going to bring up our moon again. Where's our moon? There we go. So you see these dark regions on the moon. They're called mare, which mean seas. And they're big flat areas of volcanic rock. And so we can actually see them today when we look at the moon. And they're very important because this is where all the astronauts landed. The first actual moon landing on July 1969 was actually right about here. You can see where the mouse is pointing right now. Right about, I'm just going to pause time so the moon doesn't rotate on us, but right about here, above this little dot. And this big crater here, this big dark region, the mare, is called the Sea of Tranquility. And the reason that astronauts landed on the smooth parts of the moon, these flat mare dark regions, was that if you're going to land a spaceship on a new place, a new planet, a new moon, a new whatever, you want to aim for something that's nice and smooth and flat and easy to land on. And so that is exactly what they did. Great question from Adriana in the chat. How big are the giant rocks that smashed into the moon? Well, they do vary in size, but most of them were pretty big asteroids that if they hit the Earth today, they would probably destroy all life on Earth. So one funny thing I was doing when I was looking at the bombardment thing a little bit earlier, we'll bring it up again because it's kind of fun to watch. If we just click on one of these rocks, that one's about 100 kilometers wide. This one is 95 kilometers wide. Right, so they're all pretty big. The moon itself is 3,500 kilometers in diameter. So pretty big, much bigger than most of these leftover rocks. But these leftover rocks, this bombardment era, was the time when all those 100 kilometer, 200 kilometer rocks that were just flying around, they got sucked up by the planets. Planets like Earth, Mars, even Jupiter and Saturn sucked up all those extra rocks that became part of the planets that we have today. And because they did that, there's not a lot of rocks left over in the solar system that could cause us a lot of grief today. So there you go. All right, let's go back to the Earth. Let's bring up a new Earth because we destroyed the last one by firing the moon at it. So we'll bring up our new Earth. Here it is right here. Well, let's just bring up two of them. Oh, and of course they crash into each other, and that's really bad because now they destroyed each other. Sorry, new Earths. Okay, let's get an even newer Earth. All right, you stay over there. No, I said stay over there. Okay. Alright, we'll get rid of this mostly dead Earth. There we go. Okay, back to our Earth here. We're going to fire some stuff at it. Now, what do we want to fire at it? Oh, that's a good question from James. If the moon were destroyed, what effects would we notice on Earth? Well, if the moon just... There's a couple possibilities there. If the moon was actually destroyed, if it blew up, there would be a lot of shrapnel that would fall down on Earth. And I think there's actually a good simulation in Universe Sandbox about this. So moon, I think explodes is what we're looking for. Let's bring that up. Earth exploding. Oh, here we go. Earth and exploding moon. So that's what this simulation is. So the moon is going to explode. Now, of course, the moon is much further away from the Earth than this simulation implies, but very soon the moon's going to explode. There we go. Now, if the moon exploded even 384,000 kilometers away, this kind of thing would happen. Lots of these chunks of rock that were left over from the moon would smash into the Earth over time, over probably several days, and most of them would be along the equator too, because the moon does kind of orbit along the equator of the Earth. And so very slowly but surely, all these beautiful chunks of moon would smash into the Earth and create craters that were several hundred kilometers wide in some cases, like these lovely ones here that you can see on the nighttime side. But you can see it kind of happens gradually as they slowly spiral in. As they get closer to the atmosphere slows them down. So that would be kind of a disastrous effect if the moon exploded. But there's a little bit of a difference. If the moon just disappeared all of a sudden, there wouldn't actually be a lot of changes. For one, nighttime would be a little bit darker. Right? Whenever there's a new moon, when the moon is really close to the sun, we don't see the moon up in the sky at night. It doesn't reflect sunlight, so nighttime is a little bit darker. But the bigger thing that we would notice is that there wouldn't be any tides, right? There's no more high tide and low tide, and those happen because of the moon. We talked about that a little bit last week. So no high tide, no low tide, and that's about it. The moon doesn't really do much else. It looks pretty nice. It gives us the tides, and yeah, that's about it. It's our companion as we move through space. So if the moon did explode, it'd be a lot worse, but if it just disappeared, we probably wouldn't be too broken up about it. Our calendar might be a little bit different too. All right, there we go. So let's go back and bring up the Earth again. Thanks for the questions, by the way, and to lovely people tuning in here. It's really nice to get some guidance on things that you want to see, because otherwise I'm just going to keep smashing stuff into the Earth. So let's find some big stuff. How about a small star? A small star would be kind of fun. Okay, that's a big star. Oh. Actually, that is a small star, but it just happens to be pretty big. How about Sirius B? Where's Sirius B? That's a nice one. Where are you, Sirius B? Actually, what's this guy? Oh, okay, here's a good small star. Yeah, believe it or not, this is a star. It's called PSR 2144. And we're just gonna, actually might be a black hole. Okay, we're gonna get rid of that guy. Bring up the Earth again. Let's start with you, new star. Crazy. The number of times I've had to click new simulation to try and get through all this stuff because I've made a terrible mistake and destroyed the Earth. Quite often. More often than I like. Oh, another question on the moon. Edith would like to know if the lack of moon would impact polarity. Can you explain what you mean by polarity? Do you mean like the north and south poles of the Earth? Is that what you're referencing? So yeah, you can answer that question in the chat, and then we'll take a look at it. But okay. Let's add a star. Let's find a good star. Sirius, right? Oh, that's way too big. Polaris B. Okay, that's big. Anyway, let's just put the star next to the Earth, and there it goes. Goodbye, Earth. Not as nice as we'd hoped, right? Okay, we're gonna smash things into the Earth, though. Let's find smaller stuff. It's gonna be a little bit nicer that way. Okay, so you did mean. The polarity, the north and south pole of the Earth, probably wouldn't change much. The magnetic field of the Earth happens because of the Earth's core being liquid. It's moving metal. And so that moving metal creates a north magnetic pole and a south magnetic pole, and it's not really affected by the moon. The moon doesn't have a magnetic field. Its core is frozen, it's solid, it's a chunk of rock, so it's not really affecting that at all. Okay, so to answer your question, would the lack of moon impact the polarity of the Earth? Probably not. Probably wouldn't. Okay, the biggest moons. That's a good one. Jen's asking about the biggest moons in the solar system. Well, we do have quite a few that are larger than our moon. Our moon, I think, is the 5th or 6th largest moon in the solar system. So let's get them orbiting. So there's our moon. Now we can add some larger moons. This is the moon Europa, a moon of Jupiter. We send that flying around. The two biggest moons in the solar system, I'm just going to stop these here, are Ganymede, which is that one, and Titan, which is slightly smaller. And if we just kind of move, let's get rid of our moon, let's get rid of Europa for now. So we're going to add our moon. You can kind of see, let's get a bit better view here, there we go. Oh, worry about the camera too much. but you can kind of see that our moon is a fair bit smaller than Titan and Ganymede. Ganymede's a moon of Jupiter, by the way. It's one of the 4 what are called Galilean moons. They were discovered by Galilei, a very famous astronomer back in the 1600s. And the large moon Titan is a moon of Saturn, and it's the only other moon that has, the only other body in the whole solar system other than the Earth to have a liquid cycle, meaning it has rain, it has lakes. It actually has a lake called Lake Ontario. Go figure. Except the kicker is that those are not lakes of water. It's not raining water. It's raining gasoline, methane, and ethane. So Titan has a liquid cycle, it's just not made of water. But that's a really interesting thing to study because it gives us insights about what liquid cycles might be like on other planets around other stars. Okay, so these are the 2 biggest moons in the solar system. They're actually larger than the planet Mercury. Let's see, there's Mercury. You can see Ganymede's just a little bit larger. Oops, a little bit larger than Mercury. Sorry, Titan's a bit bigger than Mercury. Excuse me, so is Ganymede. And now, because we came here to see explosions, we're just going to let time play, and we'll watch them all slowly destroy each other as they... oh, that Mercury just vaporized Titan. That was fun. Oh, look at this guy. His name is Fragment. So is his. We've got lots of fragments left over as these moons slowly destroy. It looks like Mercury's going a little bit crazy with Titan's atmosphere since it smashed into it. We may never see Mercury again. But here the moons slowly spiral in, and just like everything else that crashes into the Earth, it's leaving large craters. The temperature of the Earth right now, on average, is about 215 degrees Celsius, so a little bit uncomfortable. That's actually one of the biggest things that would happen if something crashed into the Earth that was surprisingly heavy, is even if it only crashes into one side of the Earth, the entire Earth would heat up just from the pure energy of that rock smashing into it. So it would be, it wouldn't be a very nice place to live for very long. And here we go. All these fragments are starting to spiral in a little bit more. The moon's kind of shepherding them in. Mercury's off on its own. And all kinds of fun things happen. Alright, so we'll blow up a couple more things. Let's just add something nice and big, like let's send Mars flying in. Okay, go get him, Mars. There you go. Whoa, that's a good crater. A lot more fragments. Let's see if we can fire a Mars at the moon or something. And see if we can hit the moon. And go. Oh, we missed. That's okay. It hit the Earth instead. There is some fun to just crashing things into other things, right? Oh, there's Mercury coming back with all that gas. I guess the gas from Titan was left over. So we made some nice chaos with all this stuff. There we go. Okay, so that is our first little bit of Universe Sandbox. Now, like I said, we were going to talk about a couple other things. We're going to use Universe Sandbox to talk a little bit about planets around other stars. And I want to start by showing a very important planetary system that was discovered. It's called Trappist One. So here's Trappist One. I'll try and get a nice center view. Trappist One is a star that's about 40 light years away from the sun, which means to get there would take several million years on a spaceship. So it's far away. We don't have to worry about getting there anytime soon. In fact, we can't get there anytime soon. But what's really interesting is that this star, Trappist One, actually has 7 planets. It was discovered in 2012. It was discovered to have 3 planets, and then 4 more were discovered. And the colors that you're seeing here are especially important. These colors represent what's called the habitable and inhabitable zones. So we have the habitable zones. The idea is that if a planet is really, really close to its star, it's too hot. The star's energy, its heat, boils away water and makes it unsafe for life. Because as far as we know, you need liquid water to have life. So all the heat from the star is boiling away these closer planets. They don't have any water, and if they did, it's boiled away. And so they're just not suitable for life. The planets that are way out in this blue zone, way, way too far away, like just this one here, I guess, it's too cold. It's far enough away from its star where the light from that star, the energy from that star, isn't enough to heat up all the ice and make it into liquid water. And so you have frozen water, and so it's also probably not a great place for life. However, the green zone in the middle is a place where you're not too close to the star, you're not too far away, so it's not too hot, it's not too cold, it's just right. It's called the habitable zone, and we also call it the Goldilocks zone, because if you remember the story of Goldilocks and the three bears, it was the porridge that was not too hot, not too cold, it was just right. And so there are, in fact, 7 planets, and 3 of them are in the habitable zone of this star, which is why it's a very fantastic star to study and to look at. Now, these planets, these renderings aren't actual. We don't know if they're what the planets look like, and so what you're seeing here are basically artists' impressions of the different planets. But if they do have water, hopefully somebody will find out if they do have actual water sometime in the next few years. I'm just going to change the lighting a little bit to be a little bit more reasonable. So here we go. You can kind of see that this planet, if it was a water world, it's icy and cold in the poles and nice and wet, watery at the bottom. So there you go. Another question from Jen. What would happen if other planets were as close to us as our moon? Interesting. Let's take a look. We'll come back to talking about exoplanets. Trappist is just one system, but we're going to talk about quite a few, maybe 2 or 3 more actually, and I'll show you kind of how we find planets around other stars. But let's go back, bring up the Earth again. Okay, so now I think I mentioned in a previous show that the moon is about 384,000 kilometers from Earth. So if we were to place another planet at the same distance of the moon to see what happens, we would have to go to 384,000 kilometers, which is right about there. So there's Mars at 384,000 kilometers. It's a pretty stable orbit, believe it or not. If we bring up the orbits, you can kind of see. So there's Mars's orbit. Sorry, it's a little low. Mars's orbit around the Earth, if Mars orbited Earth. It totally could. The only real difference is that in the sky, Mars would, for one, be quite a bit bigger because Mars is about 2 times as wide as the moon. And we would also have higher ocean tides, right? We would have a much higher high tide and a much lower low tide, but they would still happen at the same time of day. The Mars would still orbit the Earth at the same rate that the moon does because it's based on how far away it is. And yeah, that's about it. It would not be a destructive thing. But it would start to get a little bit crazier if we placed other planets there. So Mars does happen to be smaller than Earth, which is kind of a nice thing if you're going to make it orbit it. But let's pick a larger planet, like Neptune. And again, we're aiming for that 384,000 kilometers, which is about here. Well, that's kind of a terrible orbit. I'm gonna try that again. No, Earth, stay there. Okay, so let's add another Neptune, and we want it to orbit at 384,000. So yeah, okay. So we're starting to see the challenge already. Is that typically when you have orbits of things in space, and I'm going to say this slowly as the Earth slowly gets destroyed by Neptune. When you have orbits in space, it's not that one thing orbits another. It's that both things are actually orbiting. Oh, that was a nice explosion. It's basically that 2 objects orbit their center of gravity. The problem is that when you have something like the Sun, which has 99% of all the mass of the solar system, the Sun is so big that usually the center of gravity between the Sun and the Earth, or the Sun and Mars, or the Sun and any other planet happens to be inside the Sun. And so it really just looks like something orbits the Sun. Okay, so let's fix this a little bit. Let's actually make Earth orbit Neptune. And there you go. So the bigger, but there's one thing to note. You can see the Earth working its way around, but Neptune is also rolling around like a ball. Okay, so they're actually both orbiting something called the barycenter, or the center of gravity. And if you look at the orbit, it looks a little bit little bit off center. You can see if we speed up a little bit, you can see Neptune doing a bit of a wobble. See that wobble as it runs away from us? Get back here, Neptune. There we go. So you can't see the wobble when we're in Neptune's frame of reference, but hopefully you get the idea. If you had two things that were the same size, like if we tried to make the Earth orbit the Earth, this is where some really strange things can happen too. So let's slow down time just a little bit. I'm just going to try and center that a little bit more for everybody here. Oop, there they are. Alright, so if the Earth tries to orbit the Earth, one doesn't really orbit the other. They kind of just spiral around. It's not really a stable thing. They're kind of whipping around. We can see kind of the paths that they're taking as they spiral around each other. So, to answer the question, what would happen if other planets were as close to us as our moon? Well, in some cases, where something's bigger than Earth, like Neptune, it would destroy us. If something's smaller than Earth, like Mars, we'd basically get higher, stronger ocean tides. Okay. All right, question from Matt. Could another planet form in our solar system or galaxy? For the former, the solar system, probably not. But for the latter, for our galaxy, absolutely and all the time. So I'm going to bring up a simulation that I was looking at earlier. This is called... there actually is a new planet, sort of, in our solar system. And I'm going to bring this up. This is evidence for a ninth planet. Okay, so we have 8 planets in our solar system. Sorry, Pluto. But Neptune is the most distant. And if we look at Neptune's orbit here, you can see, Neptune's pretty far from the Sun. Neptune takes about 168 years to orbit the Sun just once. And much further past Neptune are these things called KBOs, or Kuiper Belt objects. That's what a lot of these things are. Now, one of the interesting things that scientists found about 5 or 6 years ago, actually a bit longer than that now, no, I'd say 5 or 6 years ago, is they noticed that a lot of these Kuiper Belt objects, all these guys over here, are all lined up. Their orbits are all kind of pointing off into space, way out here. Now, the only way that that could actually happen is if there's something balancing that out on the other side. And if you do the math, that other thing could be a planet. There's actually a 1 in 15,000 chance that it's not a planet, that you could get this kind of pattern from something that's not a planet. So the idea is that there actually is a Neptune-sized planet in our solar system that we haven't discovered yet, and that is our Planet 9. It's very likely to be a gas planet like Neptune. It's also likely to be very cold like Neptune, but it's estimated to weigh between 10 and 20 times as much as the Earth. It's pretty heavy, pretty big too. Now the problem is we don't know exactly what its orbit looks like. So this is a good guess based on the mathematics of these other objects, but you can kind of figure out and say, well, okay, its orbit should look like this. But then the second problem is we don't know where in its orbit it is. We don't know if the Planet 9 is here, really relatively close. We don't know if it's over on this far part of its orbit over here. We don't know if it's over here. And so that makes it a lot harder to see, because when you look up in the sky, finding something, even though it's as big as Neptune, it's so far away that it's really, really hard to spot. You're looking at a huge region of sky, and that's why it hasn't been found yet. It's very likely to be out there, and hopefully we do find it in the coming years, but right now, yeah, no idea. And a follow-up from Steve in the chat, Planet 9's proposed to weigh as much as Neptune, about that, yeah. Neptune weighs 17 times as much as Earth. Planet 9's expected to be between 10 and 15 times as much as Earth. So still, pretty big planet to be pretty far away. So that's the first half of your question, Matt. The second half of the question, could another planet form in our galaxy? And the answer is absolutely yes. We find planets in our galaxy all the time. Our Milky Way is made up of about 200 billion stars, and it's estimated that every year one new sun worth of star is born. So every year the galaxy is churning out one new star on average. And when those new stars form, as far as we know, they form planets. It's very likely now that every single star in our galaxy, in the universe, has at least one planet, which is pretty exciting. So this is our Milky Way. This is obviously going really fast. We're several million years in the future. The galaxy does rotate, but over time, every year, there's a new star being formed in our galaxy. So let's take a look at why we know that, though. I'm glad you asked that question, Matt. How do planets form? How do we find them? How do we know this stuff? Okay, and so I'm going to bring up a little image here. We're going to take a look at how we discover stars around other planets. This is really neat. What happens is, when we look at a star in the sky, occasionally what we see is the star is bright, and then it gets a little bit dimmer, and then it gets bright again. Now that can happen for a lot of reasons. Some stars actually pulsate. They get bigger, they get smaller, they get brighter, they get dimmer. They're literally just called variable stars. That happens. But the other reason that this might happen, at least to a lesser degree, is that a planet, as you can see in the image, a planet is passing in front of the star. And this is actually how we discover planets around other stars. Is we look at a star, any star in the sky, closer ones are a little bit easier, and we say, okay, its brightness is dropping just a little bit, and then it goes back up. Okay, well, if it happens again, and then again, and then again, we know, and it lasts the same amount of time and the same brightness dip is there, we know that that's a planet orbiting that star. If it happens periodically, it means the planet's going all the way around the star and blocking out that light again and again. And thousands of planets have been discovered that way. Except there's a bit of a problem. You're not finding every planet. So when we look at that star on this image, we're very lucky because the planet is passing right in front of the star. There goes the planet moving all the way across the star, blocking out its light. But what about the planets that actually go over top of the star, that orbit over top of the star? I'm going to bring you back to Universe Sandbox for a second. Actually, I'll just bring you back to me because that's fun. I'm not on as much these days, but so here's your star, and here's your planet going in front of the star, blocking out its light. But what about the planets that go like this? Hold it still there. There we go. That go over top and around. We can't actually see them going in front of their star from Earth because they don't. They don't block out their star's light at all. And so there's no way we could ever discover that planet around that particular star. We're looking for the stars that the planets, the planetary systems, are flat and lining up with the star, pointing at the Earth, so that we can see that little dip in brightness. Just one more quick housekeeping note. There's another question from Adriana in the chat. If we orbited Neptune, would we be a moon of Neptune? Probably. If we were in a stable orbit around Neptune, Earth would be called a moon of Neptune. Pretty unlikely that... and we would also be the biggest moon in the entire solar system, and we would probably destabilize every one of Neptune's 14 moons that are existing right now, which would look kind of cool, but you'd almost call it a double planet at that point. And it's pretty likely that if that did happen earlier on in the solar system, that if an Earth-sized object started orbiting Neptune, that it wouldn't be stable, it wouldn't last. It would either crash into the planet, crash into another moon, or just be kicked out and just end up somewhere else in space. So it's really hard to get big things to stay in one place for a long time, unless they're very far apart. And that's why when you look at our solar system, all the planets are really spread out quite nicely. So, I'll bring us back to our solar system here. Yeah, I mean, our solar system, the planets are spread out very nicely. There was somebody who did some math not that long ago, I say not that long, maybe a couple of years ago, based on the stability of solar systems, and basically our solar system was as stable as it could be. You literally couldn't pack any more planets into our solar system without destroying the whole thing. And so our solar system ended up stable because it was the only stable configuration for the given planets that we had. Pretty crazy. Okay, so going back to finding exoplanets. To answer Matt's question eventually about why we know there are so many planets in the galaxy is that if you add up the number of planets that pass in front of their star, like in this image, and you account for all the planets that go around their star in a different way that we can't see, you add up all of that over the entire 200 billion stars in the Milky Way, the answer that you come up with is that every single star in the entire universe should have at least one planet. And that's exciting, because that means that when you look at the stars in the night sky, every one of those planets, or excuse me, every one of those stars has a planet. When you look at the Milky Way, every star has a planet. And that is the average, which means there are probably stars with no planets, and there are probably stars with 10 or 20 or 30. That's kind of exciting. In our Milky Way, it's estimated that there are about 1 trillion planets. And so when Matt asked, could another planet form in our solar system or galaxy? Another planet can't form in our solar system, but in our galaxy, they're forming all the time. Pretty amazing. And so I'm going to show you one such planetary system that's actually really, really important, because not only is it a planet around another star, it is a planet around the closest star. And this is called Alpha Centauri. The Alpha Centauri system. The name basically means Alpha is the brightest star in a constellation. The constellation is Centaurus, which is visible in the southern hemisphere. So sadly, for us in the north, we never get to see these stars. Alpha Centauri A, this one right here, is I think the 5th or no, maybe 10th brightest star. No, 10th brightest star in the sky. I don't know for certain, but it is among the brighter stars in the sky because it's very close to us. It's only about 4 light years away or so. And it's actually a double star. About 2/3 of all stars are actually doubles or triples, which means they're born in pairs or triplets. And so Alpha Centauri A and B were born in a pair. They're not exactly the same mass. Alpha Centauri A is about 10% heavier than the Sun, and Alpha Centauri B is about 10% lighter. And so when we look at that barycenter, right, I'm just going to get rid of some trails here. There we go. Oh, we don't need to select that. There we go. When we look at this barycenter, this is the center of gravity of these two stars. And it's actually a little bit closer to the heavier star. So as these stars orbit, they go around the barycenter, and Alpha Centauri orbits closer. Alpha Centauri A orbits closer, Alpha Centauri B orbits a little bit slower. But the amazing thing about talking about the system is there's actually a third star. Way, way far out here. Oh, there it is. That is called Proxima Centauri, this guy down here. Proxima Centauri is the closest star to us other than the Sun. And it's because it's part of this system and it actually does orbit closer than the other two. At its closest, it's about 3.6 light years distant. Now, the amazing, spectacular thing about Proxima Centauri, if we zoom all the way in, it has a planet. And guess what? It actually has 2. It only shows 1 planet here in Universe Sandbox, but there's actually 2 planets that orbit the closest star to our Sun. And here's where it gets even more exciting. That planet's in the habitable zone, or just at the edge of it anyway. So we actually have a planet orbiting the closest star, other than the Sun, that could support life. Now, 3.6 light years away, 4 light years away, would still take 20 or 30 years to get there with a very fast satellite. And I'm not talking about people going there, I'm talking about little tiny spacecraft going there. This is an actual idea, is to send a bunch of tiny little spacecraft at about 1/4 the speed of light to get to Proxima Centauri and look at this planet over the course of about 20 years. We can zoom in on the planet a little bit. Again, this is an artist concept, so it's not actually what it looks like. I'm just changing the lighting there a little bit. But if this planet didn't have a tilt, it would basically have this flat area where it's really, really warm, closer to the equator, and at the poles it would be really cold. And so that would be an interesting place to live, because it would be really, really hot at the equator. All the habitable, the nice areas would be right around here, and then you get up to the poles and it's too cold and harsh. It's important to mention that, sorry for the movement there, that Proxima Centauri is actually what we call a dwarf star, a red dwarf star. And if we zoom into it a little bit, we can bring up the sun and the Earth and see just how small this star actually is. So next to the sun, there, that's Proxima Centauri next to the sun. So we bring it up there. Quite a bit smaller than the sun. Proxima is still bigger than the Earth, but it is a pretty tiny star. It doesn't have a lot of energy output. And so what that means is that for the planet to be in the habitable zone, see, it's still quite a bit bigger than the Earth. We'll just rotate it there. So there's the Earth. It's still quite a bit bigger, but that planet, Proxima b, actually orbits pretty quickly. It only takes, I think, a few hours to go all the way around. Like, let's see. Okay, a few days. So I think I'm counting about 3 or 4 days for that planet to orbit its star. So imagine having a year, which only was 3 or 4 days long. Pretty crazy. But that's Proxima Centauri. It actually has a planet in the habitable zone, the closest star to Earth other than the sun. Okay, question from Steve. Can we remove a planet or the sun to see how it will disrupt the equilibrium of the solar system? I would love to do that. So let's bring up our solar system. Here it is. All right, what to delete first? Let's get rid of the sun and see what happens. Goodbye, sun. Now, the initial thing is that it's actually going to take about 8 minutes before the Earth would notice anything. When the sun does eventually, if the sun did disappear, we wouldn't know for 8 minutes, because that's how long it takes a beam of light to travel from the sun to the Earth. And nothing can travel faster than light, which means gravity itself can't travel faster than light. So after 8 minutes, the Earth would start flying off into outer space, as would all the other planets. There's nothing to hold them, to cause them to accelerate in that elliptical orbit. And so all the planets basically continue on a straight line trajectory, as does the whole solar system, forever. The other problem is that it would get really, really cold really fast. We can go take a closer look at what's left of the Earth. Whoa, too fast. Too fast. Slow down. Okay. So now the average temperature of the Earth is about minus 15 degrees, and that's also dropping. So it's getting colder really fast. Since I last updated you, it's gone down to minus 20 degrees on average. The Earth is basically becoming a snowball. Outer space is cold. The average temperature of outer space is about minus 269 degrees. Minus 269 degrees. It's only a few degrees above what we call absolute zero. And so as all the planets move further and further out into the solar system, away from what used to be the sun in straight lines, they're all going to get really, really cold. All the water would freeze. All of our food that we grow would not be growable anymore. We would have a permanent nighttime, which would be beautiful for dark skies, but we just wouldn't last very long. So that's what would happen if the sun was destroyed. And so if we can open that again, and we'll try a different thing this time. Let's see, how else can we destabilize our solar system? One of the nice things to do is if we actually make the Earth as heavy as the sun, we can see equilibrium go crazy. Let's actually take away a planet, though. Let's get rid of Mars. Actually, you know what's an even better one? Let's get rid of Jupiter. Because Jupiter is kind of the shepherd of our solar system. If we got rid of Jupiter, you might notice that not much has really changed. Right? The planets are all in their stable orbits. So not having Jupiter is really not a big deal for the solar system. And I'm getting rid of Jupiter because it is the biggest planet, right? It should have the highest effect. But because the solar system has been around for about 4.5 billion years, it's come to equilibrium. It's not really changing very much these days. The biggest disruption would be getting rid of Jupiter, though, because Jupiter has this effect where any wild rocks, asteroids, comets that come in from really far away and could smash into the Earth, Jupiter's gravity is so strong that it often kicks away those rocks or prevents them from coming to the inner solar system and causing any damage to the Earth. So we're actually really lucky to have Jupiter, but if we didn't, we wouldn't really notice. If you want to make things get a little bit fun and a little bit crazy, if we bring this one up again, we actually increase the weight of something. So a good way to do that is if we bring up the Earth, we can actually make the Earth, let's make it 10 times as heavy. There we go. So now the Earth weighs 10 Earths. How will that change things? Not too much, I don't think. Let's try and focus in here. I thought it would have a bigger effect personally, but it doesn't really. I mean, the Earth is still really small compared to the Sun, which is so much bigger and more powerful, right? The Sun has the mass of about 1.3 million, sorry, the volume of about 1.3 million Earths. It's much, much, much heavier than the Earth. I think it's 10 to the 19 kilograms. You know what? I'm not actually sure how much heavier the Sun is in the Earth. But one thing we can do is we can make the Earth as heavy as the Sun. So let's go and now, there we go. We make the mass of the Earth exactly the same as the mass of the Sun. Now let's see what happens. All right, now all the planets are going a little crazy. The Earth actually pulls the Sun right out of the solar system. Everything's going haywire. All the other objects in the solar system start to treat the Earth like another sun. And stuff goes flying all over the place. If we go and zoom in a little bit more on the Earth, well, it's changed a little bit. The Earth has basically become a neutron star at this point because it's really compact and now really dense. And so that's cramming that much matter into such a small space has basically caused all the electrons and protons to be squeezed out of the Earth, and we're left with a giant neutron star that is as heavy as the Sun, but the size of the Earth. So that's kind of fun, as it slowly destroys the solar system. So yeah, it would definitely disrupt the equilibrium of our solar system. However, to outside observers, our solar system is just kind of its own thing. This really wouldn't cause any damage in the greater galaxy. The Milky Way doesn't really notice any difference, and it's just kind of what we end up with. There we go. Now, let's go in between a little bit, though. Let's make the Earth the weight of Jupiter. We'll say it's 1 Jupiter. Okay, so this is interesting. Did I change it? No, I didn't change it for some reason. 1 Jupiter, please. There we go. Okay, now the Earth is much heavier. The extra gravity doesn't seem to do a lot. It's probably going to start to destabilize the orbits of things like Venus and Mercury. And here you see as Venus gets closer to the Earth, its orbit's definitely getting shifted around a little bit. You can see the orbit of Venus is slowly working its way outward. It's probably also going to destabilize the orbit of Mars as well. But again, not as big an effect as I was expecting. Oh, it seems the Earth has made some changes, though. Let's go take a look at the Earth. So being... Oh, here it is. So being as heavy as Jupiter seems to have changed things a little bit. All the land seems to have disappeared off the Earth. Not sure why that happened, but there we go. It's probably pulled the atmosphere in a little bit more. I don't know. That's a weird thing. Anyway, there's lots of really crazy things that we can do. Okay, so with our last 10 minutes, I actually want to talk about black holes. I'm going to show you what a black hole really looks like and kind of how we find them. We can add them here in Universe Sandbox. They're pretty nice looking things. I could pretend that I've put one up right now, but there's nothing there. Don't worry. So let's get a black hole that there's basically 2 types of black holes, and I'll put them both up here. So a black hole. Okay, here, this black hole, and It's kind of funky looking thing. You really only notice it when it's moving. And this other much bigger black hole. So we have two types of black holes. These giant ones, 1,000,000 times as heavy as the sun, and this one 100 times as heavy as the sun. Basically, the only difference is that one is a lot smaller than the other, and it's easier to see when we have the galaxy here. You can kind of see that there's our black hole. It does distort light. As you can see, light is distorted by the black hole itself. That's a relativity thing. Gravity itself can bend light. So these two types of black holes, though, where's our big one? I think we lost it. Oh, there it is. Okay. These big black holes, called supermassive black holes, are often found in the centers of galaxies. Most galaxies have these big supermassive black holes. They also have these smaller ones. I guess you would call them normal black holes. But you see how it's really hard to see the little guy. Little black holes like this tend to be really small, really compact. And just to put it in context, this is 100 times as heavy as the sun. It's only 300 kilometers across, which makes it smaller, about 10 times smaller than the moon. So imagine you have something 100 times as heavy as the sun, but only 1/10 the size of the moon floating out in space. Chances are nothing's ever going to get close enough to it to cause any damage. It could be floating out there in the vastness of outer space and not do anything. There could be one up in the sky that we could see right now, but it'd just be so far away that it wouldn't cause us any damage. Because gravity actually changes with the inverse square law, which means if you go twice as far away from this black hole, the gravity decreases by a factor of 4. If you go 4 times further away from this black hole, the gravity decreases by 16. And so the farther and farther away you are, you don't really notice that it's there. So there could be, actually the estimate is that there's about 1 billion black holes in the Milky Way galaxy. Technically anywhere from 100 million to about 1 billion that are about that size. And probably smaller than this. This is 100 solar masses. Most of them are probably around 10. And they're just out there floating in space all over the place. But then we come up to this big guy. These supermassive black holes typically are only found at the centers of galaxies. And that's because the center of the galaxy is where most of the matter ends up over time. These black holes are older, or I should say as old as the universe in some cases. And we do have a couple questions in the chat. If we put a black hole in our solar system, Adriana, I'm going to show you that because it's kind of cool. And Matt, do black holes orbit something? Do they orbit other black holes? Technically, no. If we take a look at a galaxy, if we bring back, open galaxy. Where's the Milky Way? Just the Milky Way, please. If we bring up the Milky Way, you can see this big galaxy. In the very center is one of those giant supermassive black holes. The one that's in the center of the Milky Way is called Sagittarius A star, and it weighs about 3 million times as much as the sun. Now, when we say, do black holes orbit something? Remember when we were comparing, we were putting things in orbit around the Earth? Bigger things are orbited by smaller things. And so the idea is that if the black hole's the biggest thing, the black hole's the heaviest, I should say lighter things orbit heavier things. And so the correct answer is that the black hole doesn't orbit anything. Everything orbits the black hole. Okay? But that's not entirely 100% accurate, because our galaxy is not the only galaxy. There are these things called galaxy clusters, and this is directly to you, Matt. There are hundreds of billions of galaxies in the universe, and each one of them has a supermassive black hole in its core. Galaxies act just like planets or stars. They have gravity, and that gravity behaves the same way as gravity of planets, as gravity of stars. And so what that means is that if you had a bunch of galaxies together, like in a cluster, which I'm actually going to show you, here's your galaxy cluster. These galaxies are orbiting one another. They're colliding with one another. They're shifting and moving and changing over time, over millions and billions of years. And now it's going all crazy right now, but this doesn't happen too often. And so the answer is that do black holes orbit something? black holes and other black holes that are in the centers of these giant galaxies, they orbit the center of gravity of a cluster of galaxies. They're all doing this big gravitational dance that's been going on since the beginning of the universe and will continue for a very long time. Great question. If we put a black hole in our solar system, let's do it. Let's see. Solar system with no sun. Solar system. Here you go. Solar system with a black hole instead of the sun. Well, the good news is, okay, so let's take a look at our black hole. There's our black hole. This black hole weighs exactly the same as the sun does, except it's only 3 kilometers wide. That's the big difference. But from the point of view of gravity, nothing is different. Absolutely nothing. And so if we actually play the simulation, the planets of our solar system, and I'm going to bring up the orbits here, the planets of our solar system don't actually know the difference between the sun and a black hole. Now, let's be honest. The sun gives off light, heat, energy. So if a black hole did replace the sun all of a sudden, the Earth's orbit wouldn't change, but it would get really cold really fast. And you can see if I could show you the temperature of the Earth right now, it's steadily decreasing to -10, -15 on average. And of course, if we did zoom in on the Earth, you'll be able to see that it is now a giant ball of ice. That's slowly getting colder and colder and colder. So, there we go. I'll just let it get a little bit icier. Sorry for the rapid movement, but kind of fun. There, now we have a giant Earth-sized snowball as we orbit the black hole that weighs as much as the sun. There you go. So that's basically what would happen. The solar system, all the orbits are exactly the same. They stay in equilibrium. Gravity is exactly the same from the black hole or the sun. It's about the mass. It's the center of mass. That's what's important. The center of gravity. That's really, really important when we're talking about things orbiting other things. Okay? Now, sometimes black holes can orbit one another. They can crash into each other, and they basically form bigger black holes. But I'm actually going to show you an image that's one of my favorites. This is a picture of a real black hole. You probably saw this. This is the first picture of a black hole that came out last year, in early 2019. It took 3 years to capture. This is the first real image of the black hole. You can see the black hole itself in the center. What you're seeing around the edges is known as the accretion disk. It's actually bright. We can't see black holes because they're black. They don't give off light. They have so much gravity that light itself cannot escape. And if I was to show you that, I'm going to show you the parts of a black hole. There we go. The event horizon is the black hole itself that we see, or rather that we can't see. But that accretion disk, that's material, matter, stars, gas, dust, falling into the black hole. And as it does that, it goes around faster and faster and faster. As it does that, it actually heats up. It gets hotter. And as it gets hotter, it starts to glow. First in infrared, and then into visible light, and then into ultraviolet. And eventually it goes so fast and builds up so much heat, millions of degrees, that it can actually emit X-rays and gamma rays that we can see all the way across the universe. And so when we were to look at that last image of the black hole, you're actually seeing the light from the accretion disk that's been heating up as stuff is falling into this black hole. This black hole weighs about 5 million times as much as the sun, and it's in a distant galaxy. I can't remember which one, but it is in another galaxy, not in our own Milky Way. But this is a real picture of a black hole, and it confirms a lot of things that we knew about black holes but weren't certain of. The other parts of the black hole itself is called a singularity. That's actually within that dark region called the event horizon, and that is you can't see it because it's blocked out by the event horizon, which is the barrier where anything that crosses the event horizon cannot come back out, because in order to come back out, it would have to travel faster than the speed of light. Okay, and then finally we have this relativistic jet. That's a little bit harder to explain why that happens, but basically it goes back to something we call conservation of angular momentum, and it basically results in these huge jets of radioactive material being fired off of these black holes that we can actually see outside of an entire galaxy. So let's have some fun with the black holes in Universe Sandbox with the last few minutes that we have. We're technically at the end of the stream, but I'm going to show it to you anyway because it's kind of fun. We're going to bring up our black hole. I'm going to add a black hole that is reasonably sized. We'll say, yeah, all right, we'll say 10,000 solar masses. I say reasonably sized. That's not reasonable at all. That's huge, but you get the idea. And we're going to fire some stuff at it. Let's fire a few stars over toward it. Launch a star. Let's start with the sun. And I'm going to try and launch it off to the side to see what happens. Whoa, okay, that's fun. Maybe we should slow it down a little bit. Yeah, so basically, the long and short of it is that the sun got destroyed. You didn't expect that to happen, right? Yeah, you probably did. Okay. So, yeah, we really needed to slow down time there. But you can see the black hole there. Now this is matter that's falling into the black hole. That was, I think, showing the orbit of what was previously left of our sun. You can still see bits of sun falling in. But let's try that again. We're going to launch... We'll launch the sun once again from a bit further out this time. There we go. Now let's see what happens to the sun as it gets in closer. Remember, the sun's actually bigger than the black hole. Even though it weighs 10,000 times as much as the sun, this black hole is about 30,000 kilometers wide. The sun is 700,000 kilometers wide. And so you can see as the sun kind of works its way in, we'll take a look at the trail, the orbits. No, we don't need that. Let's go a little bit faster so we can watch the sun slowly get destroyed. Now, what happens is as the sun does get closer, we get a really overpowering effect of what's called the tidal force. Right? The same thing that causes the ocean tides on Earth causes stronger gravity on one side of the sun than the other side. And so what effectively happens is that the sun gets torn apart piece by piece along the axis that's pointing toward the black hole. This is how stars get devoured by black holes. And what a great way to finish off the show, huh? As that material falls around the black hole, the star slowly destroyed. Speed it up a little bit. And now the sun does survive that first pass, but it's actually going to go quite a bit further away before it comes back. So we'll watch it go a little bit faster as it gradually gets destroyed piece by piece as it works its way closer to the black hole. And there it goes. That's basically bits of sun are left over. With every pass, a little bit more of it gets destroyed. There we go. And you end up with an accretion disk that, when viewed from far away, looks like this. This is how black holes devour things in space, and yet still look like black holes. All right, so there we go. That was a lot of fun. I think we're going to call it here. So I'm going to just say a quick thank you for tuning in. Thanks for all the great questions. It's nice to see so many friends at least tuning in to enjoy it. I'm just doing this because it's fun to talk about space. But if you do have any other questions that you want to submit or see, I'd love to talk about them. The next stream is going to be Tuesday at 7 p.m. Jesse Rogerson is going to be back on. We're going to just be talking about whatever we feel like. So we'll take suggestions as they come in. But other than that, if you have any follow-up questions, feel free to tag me on Instagram, Facebook, Twitter, all of the three, at AstroInAction. Hope to see you again soon. Have a great night. Bye. Ending stream.